All right, let's talk about something that's happening every single time you run a piece of code, but you almost never see it. We're talking about a program's memory. You can think of it as the invisible blueprint, the architecture that holds up everything your code does. And to get started, let's just ask a really simple question.
Think about it. You write all this code, you hit that compile button, you run the program, but then what? Where does it all go? Where does all that logic, all your variables, where does all the magic actually happen inside the machine? That is exactly the map we're going to lay out today.
And look, this isn't just some boring theory class. As the source material points out, knowing this stuff is absolutely crucial. It's the bridge that connects the code you type on your screen to what the computer hardware is actually doing.
So why should you care? What's the payoff? Well, when you understand this blueprint, you can start writing way smarter, way more efficient code. You'll be able to hunt down those really nasty, complex bugs so much faster. And you can seriously crank up your program's performance. Honestly, this is the kind of knowledge that really separates the pros from the pack.
Okay, let's do it. Time to unroll that architect's blueprint and take a look at the grand design of a program's memory map.
So let's zoom all the way out. The main memory, the RAM that your program gets to use, it's basically split into two big distinct worlds.
On one side, you've got kernel space. This is the OS's private club. It's reserved for the operating system to do its thing. Think of it as the command center. But on the other side, you've got user space, and that is our playground. It's where our application actually lives and breathes. From here on out, we are going to be living exclusively inside user space. So now that we're inside our territory, what's the layout? Well, it's divided into 5 key areas or segments, all neatly organized by memory address. We've got the text, data, BSS, heap, and stack. Let's think of these as the different floors in our program's building, and we're about to take a tour, starting from the ground up. Every good building needs a solid foundation, right? Well, in our program, that's the static memory. These are the parts of our program that are pretty much set in stone the moment it launches. First up, at the lowest address, is the text segment. This is, and I mean this literally, your code. It's the raw, compiled machine instructions that the CPU reads. It is the instruction manual for your program. And just like a real instruction manual, you don't want anyone scribbling in it, so it's marked as read-only.
Okay, next floor up, the data segment. This is home for any global or static variables that you've given a value to right in your code. So if you write something like int global count equals 100, that 100 gets stored right here before the program even starts.
And right next door is the BSS segment. It's a funny name. It stands for block started by symbol, but its job is simple. It's for all the other global and static variables, the ones you didn't give a starting value to. The system just makes sure they all start out as 0. It's actually a clever optimization, so you don't have to store a bunch of zeros in the actual program file.
All right, the foundation is poured. Now for the really exciting part. Let's move up to the workshop. This is where the dynamic duo of the stack and the heap live. And trust me, this is where all the action happens when your program is running.
So if those first few segments are the quiet, unchanging foundation of the building, the stack and the heap, they are the busy, noisy workshop floors. As programmers, we spend most of our time thinking about these two because this is where data is constantly being created, used, and thrown away.
Now, this is maybe the most important architectural detail of the whole building. The stack and the heap grow towards each other. The stack starts at the top at the highest memory address and grows down. It handles things automatically, like local variables in your functions, on a last in, first out, or LIFO basis. It's super fast, but it's also relatively small. The heap, on the other hand, starts at the bottom and grows up. It's a huge, wide-open space for data you need to manage manually. Think big objects or data you need to stick around for a while. So you have these two massive dynamic forces on an inevitable collision course.
Which, of course, leads to a very important question. You've got these two powerful forces growing and shrinking inside a limited space. What could possibly go wrong?
You've probably heard of this one. Yep, a stack overflow. And no, it's not just a handy website for getting answers. It's a real and really common program-ending crash that happens when the stack simply runs out of room. So here's how it goes down. The classic example is infinite recursion. Every single time a function gets called, a new frame with its local variables gets pushed onto the stack. Now imagine a function just calls itself over and over and over without end. With each call, a new frame is added. The stack grows down and down and down until it crosses its boundary. And boom! Your program crashes. Stack overflow. And don't think the heap gets off scot-free. It has its own set of problems, like a heap overflow. This is often caused by something called a memory leak. That's when you keep asking for memory from the heap, but you forget to give it back when you're done. It's like booking hotel rooms and never checking out. Eventually, you run out of rooms.
So we've seen the blueprint, we've toured the workshop, and we've even seen how it can all come crashing down. So what now? How does knowing all this make you a better architect of your own code?
Here's the big picture. Your program's memory isn't just some random chaotic pool of bits. It's a highly organized structure. You've got that fixed foundation, your code and global variables, and then you have the dynamic workshop. The key is knowing when to use the stack, which is super fast and automatic for short-term data, and when to use the much larger heap, which gives you manual control over long-term data. Understanding this distinction is absolutely fundamental to preventing nasty bugs, crashes, and even serious security risks.
And that really brings us to the final thought. You now have the architect's blueprint. You can see the structure, you know the rules of each floor. So the question I want to leave you with is this. Are you going to consciously manage your program's memory, or are you just going to let it manage you?